Hello, I'm Michael Vunch. I'm the plant pathologist at the North Dakota State University Carrington Research Extension Center. I'd like to take this moment to share with you what we have learned about calibrating fungicide droplet size relative to canopy characteristics for improved white mold management in kidney beans. We started this research on the basis of research conducted in soybeans, where we found that calibrating the fungicide droplet size relative to canopy characteristics enables us to sharply improve white mold management in soybeans. We achieved By calibrating our droplet size relative to canopy characteristics, we achieved increases in the yield gain conferred by the fungicide of 50 to 100%. This means in many cases, we've doubled the yield gain conferred by the fungicide just by getting the droplet size right. The application rate of the fungicide was the same. The fungicide applied was the same. The application costs were the same. All we did was get the droplet size right. Naturally, we wanted to know whether we could apply these lessons to kidney beans. I'd like to give a little bit of background before I proceed into explaining our methods and our results. When somebody refers to the size of a spray droplet, they're referring to the diameter of that droplet. If you cut that diameter in half, you actually end up with 8 times as many droplets, because then we're talking about volumes. And the volume, for instance, of a 500 micron droplet translates into the same volume of 8 250 micron droplets. And if you cut that droplet size in half again, you get 64 droplets, all with 125 micron diameter. So what does this mean in terms of disease management? Local, modern fungicides have local systemic movement. What this means is that they can move upward from the point of deposition in the water conducting cells, but they can never move downward. So if we take that 500 micron droplet and imagine that it hits a leaf, take the picture on the top. What you can see immediately is that the bottom part of that leaf is going to be unprotected, because the fungicide, even though it's a modern locally systemic fungicide, it can only move upward from the point of deposition, and it may not even move to the very tip of the leaf. The extent of upward movement is dependent on the chemistry. So, but in the best case scenario, with that one droplet on that leaf, you get that fungicide moving to the tip of the leaf, which leaves you with, at best case scenario, about 2/3 of the leaf protected by the fungicide. The other third unprotected. If we cut the droplet diameter in half, suddenly we have 8 droplets, and if we spray those 8 droplets out there and we get the same volume of fungicide deposited on that leaf, you'll see that those 8 droplets are going to be distributed better across that leaf. And again, if we get this local systemic movement upward from the point of deposition, that provides you protection for over a minimum of 90% of that leaf now, given how those particular droplets got deposited in this picture. If we cut that droplet size diameter in half again, and we have those 64 droplets, and that same volume is deposited on that leaf, just by pure chance, those 64 droplets are going to be distributed much more evenly across the surface of the leaf. And when you get that local systemic movement, it's going to give protection to virtually all of that leaf. So the reason why fungicides are optimized with fine droplets is because of the coverage question and the local systemic movement. The fungicide never moves downward from the point of deposition, it only moves upward. But optimizing your fungicide performance with fine droplets assumes that those fine droplets can get to the plant tissues that are susceptible to disease. And fine droplets do not have the velocity to penetrate a dense canopy and white mold. So how did we do this research? We did this research with TJet nozzles, and we selected TJet nozzles simply because most growers and crop advisors in North Dakota and Minnesota use them and are familiar with them. In this case, we used extended range flat fan nozzles, and that choice was simply driven by the fact that we could achieve our target droplet sizes and with the driving speeds and spray volumes that we need to use for the study. We selected the nozzles and application pressures on the basis of the charts in the TJet catalog, and then we verified the actual droplet size spectrum produced by asking Winfield United to test the spray pattern with their laser-based system in their wind tunnel in the R&D facility in River Falls, Wisconsin. What we found is that the droplet size, target droplet size for medium and coarse was spot on. But the nozzles and pressures that we were using to create fine droplets were actually producing a droplet size that was right at the boundary of fine and medium. And so either we were achieving a fine droplet on the coarsest end of the medium spectrum or a medium droplet on the very fine end of the medium spectrum. In either case, we still achieved droplets that were much finer than our medium or coarse droplets, and so the integrity of the study was intact. But what this indicates is that what you'll see in the results are basically the best case scenario for a fine droplet, because we were applying droplets that were as coarse as they could be and considered to be in the fine spectrum. If you had droplets that were even finer, i.e. in the middle or the lower end of the fine spectrum, you could expect even greater differences. We conducted testing in Carrington and Oaks, North Dakota. I know the slide just says Carrington, and that's a typo. Row spacing was either 14 or 28 inches, depending on the study. Seeding rate was 90,000 viable seeds an acre. All the treatments were applied with a tractor-mounted sprayer equipped with a pulse width modulation system. We used the pulse width modulation system to keep a constant driving speed and a constant spray volume within that study. That driving speed was either 6, 10, or 10.5 miles an hour, depending on the study. Spray volume was always 15 gallons an acre. We used 8 to 17 experimental replicates, depending on the study, and we used a large number of experimental replicates because white mold tends to be spatially inconsistent. And by using a large number of experimental replicates, we maximize the probability that every treatment will end up, just by pure chance, on areas of high disease pressure versus low disease pressure the same number of times. White mold was assessed at or near driving maturity by evaluating every plant individually in a minimum of half of the rows per plot for the percent of the plant impacted by white mold. And then harvest was conducted simulating knifing. We clipped the plants at the base, windrowed them, and allowed them to dry down, and then passed the clip drivings through the combine. We did this rather than straight harvesting because we wanted to eliminate any bias caused by any differences in lodging, any difference in standability of the dry beans across the footprint of the study. Supplemental irrigation was applied as needed to establish the white mold disease pressure needed to evaluate fungicide performance. A little more detail on our methods. This chart shows which studies were conducted at a 6 mile an hour driving speed versus 10 versus 10.5 miles an hour. In which studies we used the XR11004 nozzles versus XR11005s for the fine droplets. It also shows the fungicides that we applied. In this case, we always applied Topsin at 40 fluid ounces as our first application, followed by Endura at 8 ounces. The interval between those applications depended by the study, and the number of experimental replicants depended by the study. As I mentioned before, pulse width was modified as needed to maintain the same driving speed and spray volume across droplet size treatments. We conducted this pulse width modulation calibration manually. What we did was we actually collected the spray output from every nozzle after running the sprayer for precisely 10.0 seconds. If that spray output was a little bit too high or a little bit too low for our 15 gallon acre spray volume, we adjusted our pulse width until the spray output was perfect. In this way, we ensured that the spray volume was precise. We did this calibration of droplet size of pulse width. We did this calibration of pulse width after the fungicide was mixed and immediately before spraying the treatments. So this was done with a fungicide in the tank. We made the applications with this tractor-mounted sprayer. You'll see that there's a driving pass for the tractor. This driving pass was established with a strawberry cultivator to ensure a very smooth surface. We needed to have a smooth surface because we cannot afford to have that boom swaying. By having a smooth surface, the boom is very consistent. And that consistent boom height allows us to maintain the target 20-inch distance between the nozzles and the canopy recommended by the nozzle manufacturer for 110-degree nozzles that we utilized. We sprayed a 10-foot width, and that 10-foot width has nozzle overlap from adjacent nozzles. What you'll notice as I play the video in the next slide is that the sprayer operator, in this case, turns on the boom right before he gets to that blue flag. And then he does not turn off the boom until he passes the next blue flag. Between flags of the same color are our treatment plots. Between flags of different colors are short distances that allow the sprayer operator to turn on and off the boom while maintaining driving speed. Now, those distances where we turned on and off the sprayer were never assessed for disease severity or yield. They're outside of the treatment plots. They purely exist to allow the sprayer operator to turn on and off his boom while maintaining driving speed. Okay, so what did we learn? I'd like to start with the kidney beans seeded to wide rows, 28 inches in this case, but these results are directly applicable to 30-inch rows. We had 3 studies and that we conducted with kidney beans seeded to wide rows. And what I've done is I've highlighted in a yellow light brown color the highest yield across treatments in each of those studies. I've also presented bar graphs and a scatter plot showing the combined analysis across studies. What you can see immediately is that in none of these studies were fine droplets followed by fine droplets optimal. Instead, we consistently achieved maximum yields by applying with coarse droplets in each study. Yet, if you look at the combined analysis, you can see we do not have statistical separation. The lack of statistical separation is because we have only conducted 3 studies. In our droplet size work conducted on soybeans, as well as other crops and diseases, we look for consistent results across studies, and then we generally need 5 or 6 studies before we achieve statistical separation. What we see here are the consistent results. What we need are additional studies further proving the consistency or validating these initial results before we can develop rigorous recommendations. But in the interim, we can develop a preliminary recommendation suggesting that coarse droplets followed by coarse droplets may be optimal for kidney beans seeded to wide rows. Now let's stop back and think about this. These results make sense. When we seed to wide rows, we have very tight spacing of the kidney bean plants within the row, unless you drastically drop your seeding rate. In this case, we seeded at 90,000 viable seeds an acre, and we had very tight spacing of the plants within the row. What this means is that the canopy is very dense within the row. In order to penetrate a dense canopy, you need droplets with velocity, i.e. coarse droplets. And you notice the one study where we had some flexibility on droplet size was the study where, i.e. there was not that much of a penalty to spraying with finer droplets, was the study conducted in 2024 with Pink Panther kidneys, where the canopy closure averaged just about 50% in both first application and second application. 40% average canopy closure in the first application, 52% in the second, i.e. about half of the ground was still showing between the rows. So the study where we saw the least advantage to using those coarse droplets in both applications was the study where we had the most open canopy. That makes sense. But even there, we still optimized. with coarse followed by coarse droplets. So again, we need to have testing from additional studies before we can have rigorous recommendations. But what you see here are consistent results across 3 studies, strongly suggesting that you do not want to spray with fine droplets at both application, that coarse followed by coarse droplets are going to be optimal in most situations in kidney beans seeded to wide rows, and you would only consider a finer droplet if the canopy is very open. What about kidney beans seeded to narrower rows? I'd like to start with testing conducted with kidney beans seeded to narrow rows where the canopy was near closure at the first application, and then the canopy was dense or lodged at the second application. So look at the canopy closure in application number 1, and what you can see is that we averaged 91 to 95% canopy closure in that first application, and in the second application we averaged 94 to 99% closure. So in both of these applications the canopy was at or near closure. When the canopy is at or near closure, it becomes more difficult for a fine droplet to penetrate. Next, I want you to look at the height. You notice that with the exception of Carrington in 2021 with Pink Panther kidneys, the height of the canopy increased very little between applications 1 and 2, and actually in one of the studies the height went down. What this suggests is that lodging was likely an issue, and in the one study where we quantified it, yes, there was quite a bit of lodging with that canopy already a third of the way from vertical, with 32% average lodging. So what these results indicate is that both applications the canopy was at or near closure, and in that second application we had either a documented lodging issue or suspected lodging issue. Where do we optimize with droplet size? You'll notice again, in none of these studies did we optimize with fine droplets followed by fine droplets. Instead, we optimized with either medium droplets in the first application followed by coarse, or coarse droplets in both applications. And the difference between those two was small. So, what about the situation where the canopy was at or near closure in the first application, but we didn't have a whole lot of lodging and the canopy was really tall and upright in the second application? We had 2 studies that fit those parameters. In those studies, we optimized with medium droplets in both applications. What about kidney beans seeded to narrow rows and the canopy wide open in both applications? In this particular study, canopy closure averaged only 80% in the first application. That means 20% of the ground was still showing between the rows and between plants. If you look down right above the canopy, right down, and saw how much ground was still showing, that canopy is still wide open. And in the second application, still 15% of the ground was still showing. Average canopy closure was only 85%. So in this case, in both applications 1 and 2, the canopy was open. In an open canopy, it's not nearly as hard for fine droplets to penetrate. And remember, fine droplets maximize coverage if you can get them to your target. So where do we maximize our yields? We maximize them with fine droplets in the first application, followed by medium droplets on the second. Why medium on the second? Well, you can see the canopy closure is a bit more, and then notice the lodging. There's quite a bit of lodging with a canopy more than a third of the way from vertical. If that canopy were more closed, you would have needed coarse droplets. But in this case, the canopy was quite open, and thus the medium droplets were sufficient. So, these are results from a single study. We cannot have full confidence in these results until we conduct follow-up testing and see parallel results across studies. Yet, these results make perfect sense. So, I would like to now present a very succinct decision-making process for optimizing fungicide droplet size relative to canopy characteristics in kidney beans based on what we have learned from our studies thus far. If the kidney beans were seeded to wide rows, we optimize with coarse droplets in both applications. I would only deviate from this if the canopy was extremely open within the row, because the coarse droplets make sense, because within the row the canopy tends to be quite dense, even if you still have ground, even significant ground, showing between the rows. If the kidney beans were seeded to narrow rows and the canopy was near closure at both applications and exhibiting significant lodging or significant density due to lots of trifoliates by that second application, we optimize with either medium or coarse droplets in application 1, followed by coarse droplets in application 2, and the difference was small. So your decision is only medium or coarse in application 1, and then you know coarse in application 2 under this scenario. If the kidney beans were seeded to narrow rows and the canopy was near closure at both applications, and the canopy was mostly upright at the second application with very little lodging, we optimize with medium droplets at both applications. Finally, if the kidney beans were seeded to narrow rows with the canopy open at both applications, we optimize with fine droplets in application 1, followed by medium droplets in application 2. What you can see is that the decision-making metrics for kidney beans seeded to narrow rows were contingent on the degree of canopy closure in the first application, and then in the second application on the degree of canopy closure and the degree of standability of those dry beans. The more closed the canopy, the coarser the droplet you need. The more lodged the canopy, the coarser the droplet size you needed. These should, however, be considered preliminary recommendations. We saw consistent results across studies within the studies exhibiting these canopy characteristics. Yet, we only conducted testing within each group of canopy characteristics just 1, 2, or 3 times. And that isn't enough to develop rigorous final recommendations. In my experience in this droplet size testing, it is common to see these consistent results, and we do not achieve the statistical separation until we have run 5 or 6 studies with that particular canopy characteristic. So these results are consistent with what I've seen in other crops and other diseases. Consistent results without statistical separation until you get to a fairly large number of studies. As such, I have quite a bit of confidence in these results. Yet, until we do more testing, I cannot provide final recommendations. I would stress that these are results obtained from testing conducted with T-jet nozzles. We used extended range flat fan nozzles simply because that's what worked in the study. I would expect parallel results for all the different nozzle types manufactured by T-jet with the same droplet size at maximums. I will give you the warning, though, that as you move across nozzle manufacturers, the droplet size optimum may be different. In our testing conducted in other crops, the droplet size optimum for Wilger tends to be 1 step higher in many cases than T-jet. So where you optimize with a medium droplet on a T-jet nozzle, you'll optimize with a very coarse on a Wilger. We'd have to conduct that testing on kidney beans to develop recommendations for Wilger on kidney beans, but to suffice it to say from our testing and other testing that I would expect the optimum to be different even as the relative difference between different droplet sizes would remain consistent. Finally, I'd like to thank my staff. Aaron Faust, Joanne Collis, Jesse Hafner, and Gabby Henson in Carrington, Heidi Esslinger, Spencer Esslinger, Leonard Besman, and Kelly Cooper in Oaks. These individuals put in very long hours, are very dedicated. It is with their dedication that this work is possible. I'd also like to give some very sincere thanks to the 3 funding agencies that provided the funding necessary to pay the salaries of these staff as well as the various costs, other costs associated with executing these studies, equipment repairs and supplies. These 3 funding agencies are the North Harvest Bean Growers Association. These are your checkoff dollars. the North Dakota Crop Protection Product Harmonization and Registration Board, administered by the North Dakota Department of Agriculture, and the USDA Specialty Crop Block Grant Program, administered by the North Dakota Department of Agriculture. Again, these three funding agencies have funded this work and made it possible. I would also like to thank the private companies that do contract testing with us, because it is that contract testing that allows us to generate the revenues needed to purchase the farm equipment necessary to execute these studies. It's with those funds that we purchased the tractor that we used to apply the treatments, as well as that sprayer, as well as the combine used to harvest all the trials, and a lot of our other equipment. Finally, I'd like to give very sincere thanks to Bollingberg Seeds, Green Valley Bean Company, and Kelly Bean Company out of Hatton, North Dakota. These three companies donated the seed for our dry bean white mold research studies, and we are very grateful for them for their support. So if you see Kurt Bollingberg, John Berthold, or Dean Nelson, tell them thank you. With that, thank you for your time and attention. It is my hope that these research results will help improve your operations and reduce losses to this disease. Thank you for your time.